Let's try one more experiment here. Let's switch this one to water. Well, now we're going water into water, so we should see no difference, just shoots straight through there. But let's switch this one to air. So now it's like you're standing, you're underwater, looking up into the air. Okay, so if we do that, you can see that there is still the same thing going on. There's still refraction. It's just that in this case, the angle of incidence is smaller than the angle of refraction, because in the rare medium, everything is bigger. The angle is bigger, the speed is bigger, the wavelength is bigger. Let's change this angle a little bit. You can see that as we change it a little bit, the angle of refraction is rapidly changing. And here suddenly it's gone. Light isn't going into the air at all. It's just reflecting off the barrier here. So let's take a little look at what's happening. So notice that there's always reflected light and refracted light. And over here, the intensity of the reflected light is much smaller than the intensity of the refracted light, or the transmitted light. But as we change this angle, that balance changes. More and more of the light is reflected, and less of it is actually making it into the new medium. And then at some point, at some special angle, suddenly there is no refraction, there's no transmission of light into the new medium, there's only reflection. This is called total internal reflection, and it happens at a certain special angle called the critical angle. And in our case, the critical angle happens at about, well, here's 45, so it happens at almost 50 degrees, 48 point something degrees. That's the critical angle. That's kind of the boundary between some transmission and no transmission, only reflection. So this only happens in very specific circumstances. So notice that I had to switch it from from air to water to air. If we do it the other way around, air into water, there's never an angle where there's no transmission. I mean, unless you just shoot the water directly along the surface, but that doesn't really count. The angle of incidence then is 90 degrees. Then nothing is going in anyway. But because the angle of refraction is smaller than the angle of incidence, you're always going to get some light transmission into the new medium. So it only works if you're going from a dense medium into a rare medium. Let's check for glass. So glass is denser than water is. You can see the index of refraction is 1.5 instead of 1.33. And so let's try this experiment again. Oop, gone. So right there is our critical angle. The critical angle again is the angle at which there is no transmission of light, only reflection. There's no refraction, only reflection. And so in this case, this would be 43 degrees or something like that. So we have a smaller angle of incidence that results in the critical angle than if we were using water. So the denser the medium, the smaller the angle of incidence that will result in total internal reflection. Now let's just go to custom over here, and we're going to just make it as big as we possibly can. And so now, if what I was telling you is true, there. Our critical angle is about there. It's just under 40 degrees now. And so the larger the index of refraction, the smaller an angle of incidence is needed to make that critical angle happen. We're going to try one more experiment here. We're going to use a prism. Now you may have seen that when a prism accepts white light, it often splits it into many colors. Well, why does that happen? So if we're shooting white light into here, see that we get a rainbow out the other side. So notice that inside the prism, the light is bending. We've got refraction going on. So the light is changing speed. It's also changing wavelength, if you remember. And then as the light leaves again, it refracts again, changing speed once more. And so the different wavelengths of light are changing speed different amounts. And that's why they split into all the different colors. Because white light just contains all the colors of light, all the different wavelengths of light. And so when you make it change directions enough times, it's going to split into multiple colors. And so you've probably experienced this in your home as well, when normal ambient light or sunlight goes through some glass at just the right angle, you'll see that it splits into a rainbow. We're going to put some numbers to this idea of the critical angle. So the critical angle is just an angle of incidence that causes no refraction, or that causes rather an angle of refraction of 90 degrees. So here's exactly what's going on. We've got a boundary between two mediums. We're going to make it horizontal like that, and here's our normal line. And so we have an angle of incidence of 39.521196636 degrees. Now you might ask, why so specific? Well, we're going to see why so specific. So I'm just going to write 39.5 degrees because I can't be bothered to write all of that. 39.5 degrees, except it's incoming like this. And so we're going to find an angle of refraction of some kind. So we're going to use our relationship with indices of refraction. N1 sine theta 1 is equal to N2 sine theta 2. And we're going from diamond into sodium chloride. Okay, so we're going to look both of those indices of refraction up on our formula sheet, and it turns out that diamond is 2.42 and sodium chloride is 1.54. I do not know why a diamond would be right next to a piece of salt, but let's go with it. So 2.42 times the sine of 39.5 degrees equals, again, we're going to actually use the whole number, 39.521196636, just to make sure. And we're trying to solve for theta 2. Okay, now when we do that, we're going to multiply these two things, divide by 1.54, and then do the inverse sine of whatever that was. And we end up with a theta 2, or an angle of refraction, of 90 degrees. 90 degrees on the dot. And so if we would diagram that out, the 90 degrees is between the normal line and the wave ray. And so this being the normal line, our wave ray then would be running straight along our boundary, right? So this right here would be theta 2, or the angle of refraction. But if the light is running right along the boundary and you were standing in the second medium, you wouldn't see it, right? It would be running along the boundary of the two. And so this angle, this 39.5 degrees, this is called the critical angle for a change from diamond into sodium chloride. Now that's not a very useful transition, diamond into sodium chloride, but diamond into air, that's a useful one. Glass into air, water into air. So those are all common ones. And so the critical angle is just whatever angle of incidence causes a 90 degree angle of refraction. And so we can calculate the critical angle for whatever transition we want to do. Okay, but first, the critical angle is the angle that causes the angle of refraction to be 90 degrees. That's important. Okay, it's not the critical angle that's 90 degrees. That's important. It's not the critical angle. It's the angle of incidence, that's the critical angle, that causes an angle of refraction of 90 degrees. Okay, so if the angle of incidence is less than the critical angle, then you're going to get refraction of some kind. Okay, then the light is actually going to make it in to the medium. Refraction will occur. We've also been using the word transmission. So transmission is just the general term for one thing going into another. For light going from one medium to another, it's being transmitted into the new medium. But refraction is also occurring during that transmission. Now, if the angle of incidence is greater than the critical angle, then we get that total internal reflection I talked about, where the light doesn't transmit at all. It doesn't go into the new medium. It only reflects back into the original one. So this is total internal reflection. And like we said, total internal reflection only occurs under certain circumstances. You have to be going from a dense medium to a rare medium. So the incident index of refraction has to be greater than the refracted angle of incident index of refraction. We also have to have an angle of incidence that is greater than the critical angle. So the critical angle is just that special angle of incidence that would cause a 90-degree angle of refraction. And so if the incident angle is greater than that special angle, that cutoff point, then you get total internal reflection. So we're going to calculate that critical angle for a transmission from light from heavy flint glass to ethyl alcohol. And so we're going to use this N1 sine theta 1 is equal to N2 sine theta 2. That's real messy, but I hope you'll forgive me. N1 sine theta 1 is equal to N2 sine theta 2. And so heavy flint glass to ethyl alcohol, we can just look up N1 and N2 on our formula sheet, and it turns out that that is 1.65 for heavy flint glass, and it's 1.36 for ethyl alcohol. Theta 1 is the angle of incidence. Theta 2 is the angle of refraction. And if we remember, the critical angle is the angle of incidence that causes a 90-degree angle of refraction. And so what we need to do is put in 90 degrees for the angle of refraction. And we're searching for this one. What is the angle of incidence that causes a 90-degree angle of refraction? Whenever you're asked to calculate the critical angle, it's always asking you for what is the angle of incidence when the angle of refraction is 90 degrees. And this is usually pretty simple to do because the sine of 90 degrees is just 1. And so 1.36 times 1 is what we're getting on that side, and 1.65 times the sine of theta 1 on this side. And so I just have to divide by 1.65 in order to figure out the sine of theta 1 and then do the inverse sine. So theta 1, or that critical angle, the angle of incidence, is equal to the inverse sine of 1.36 divided by 1.65. Because multiplying by 1 doesn't really make a difference to the math. And you're going to find that it actually always works this way. You're just taking N2 divided by N1, and you're doing the inverse sine. That gives you the critical angle between two mediums. And you're going to find that if you're trying to go from a light medium into a heavy medium, which is not the way that it works, you'll get an error. It won't work. There won't be such a critical angle. And so we get theta 1, in this case, the angle of incidence that causes a 90-degree angle of refraction is 55.5 degrees. That would be the critical angle.